And bringing us back to our equation, we're going to talk about factors that affect the stroke volume now. Now, can anyone remind us what stroke volume is? Can anyone remind us what stroke volume is? Right, good. So how much blood the heart is pumping out with each heartbeat? All right, that's our stroke volume. Or how much blood the heart is pumping out, period. Right? And so the factors that affect the stroke volume are ventricular contractility. This is how hard the chamber is working, how vigorously the muscle is contracting. The second factor is end-diastolic volume. That's how much blood was filled into the chamber at the end of diastole. And then the third factor is afterload. And afterload is essentially the resistance that's found in the vessels. Okay? Now, in terms of explaining each of these points, we know that ventricular contractility is how forceful the heart is working. And it should stand to reason that if the heart is generating more force, generating more tension, it's going to expel more blood. So as the heart works harder under the innervation of the sympathetic nervous system, it's going to generate more force and expel more blood. Now, the mechanism by which it does so, there are 4 specific actions that the sympathetic system does within a ventricular contractile cell. So now we want to remember here that we're talking about a different cell. We're not talking about a pacemaker cell. Okay? And so the role of calcium in a ventricular contractile cell, I mentioned this time and time again, the role of calcium in this cell is more so for the actual cross-bridge cycling. All right, so the opening of those calcium channels is to allow calcium influx, which is a part of the cross-bridge cycling. So let's talk about those 4 mechanisms by which the ventricular contractile cell increases heart rate or increases ventricular contractility. The first one is that protein kinase in this sequence of events is going to open up the L-type calcium channels, which are slow calcium channels. And that allows calcium to come in. More calcium means more cross-bridge cycling, which means more force. Okay, we should know this from our discussion of this phenomenon with skeletal muscle. More cross-bridge cycle equals more force. The second mechanism is by activating the calcium channels on the sarcoplasmic reticulum. And by doing so, we have more calcium moving out from the SR where it's being stored into the cytoplasm. So that's the second mechanism by which the sympathetic nervous system increases ventricular contractility. The third mechanism is that it actually binds onto troponin, removes that tropomyosin from the binding sites, and causes the muscle to contract. So the actual muscular contraction is brought about by calcium within the cytoplasm. Okay, and so the more calcium we have, the more effectively, the more efficiently, the more vigorously this muscle contracts, and we increase ventricular contractility. The fourth mechanism is by increasing the calcium ATPase pumps on the SR. Again, something we've seen already. Having more calcium pumps on the SR increases the rate with which this muscle can relax. And we know if the muscle relaxes faster, it's going to contract faster as well. So increasing the rate of calcium ATP, increasing the presence of calcium ATP pumps on the SR increases how fast the muscle can relax by pumping that calcium out, which also increases the ventricular contractility. All right, so these 4 mechanisms are how the sympathetic division of the nervous system increases ventricular contractility. And when we compare the amount of tension, the amount of force that's generated by cardiac muscle at rest with the amount of tension that's generated under the influence of a sympathetic activity, we can see that it's significantly more. So with a shorter amount of time, cardiac muscle can generate more force with the sympathetic system more involved or more engaged. And this will hold true for the parasympathetic as well. We have the parasympathetic system involved, we're going to generate less tension, and we're going to take more time to do it. All right, let's talk about the parasympathetic system. Now, I mentioned this on the first couple of slides. The parasympathetic system does not innervate contractile cells. And so the significance or the influence here is negligible. The parasympathetic system does not have much to do with how hard the heart works. That's exclusively for the sympathetic division. Okay. And then hormones, very similar to the way the hormones affected the heart rate, they also affect the contractility. Epinephrine is going to bind to those beta 1 receptors, and that whole cascade of events that we talked about before is going to be brought about. Other hormones that influence the contractility are thyroid hormone. This is why persons with hyperthyroid typically have tachycardia, which is that very fast heart rate. Their heart typically beats much harder because of that increased contractility with thyroid hormone. Insulin is another one, and then glucagon. All right, and we're not going to talk about the mechanism of how these hormones act, but you just really want to understand that these three hormones can increase the ventricular contractility, which is basically how hard the heart is working. All right, and so the last factor we'll talk about is the end diastolic volume here, and this is the amount of blood that was filled into the ventricle. Okay, so at the end of diastole, this is where the ventricle filled as much blood as it can from the atria, and so it's going to stretch. That chamber is going to stretch significantly. This introduces Starling's law. So Starling's law says that if we stretch the heart chamber, if we stretch that ventricle by filling blood into it, we're going to stretch the muscle fibers. Now, the muscle fibers of cardiac muscle are different from the muscle fibers of skeletal muscle. And so at their optimal length, they're going to generate more force. The difference is with skeletal muscle, its optimum length is in the middle, right? It can't be too big and it can't be too small. We already studied this. The optimal length for skeletal muscle is right in the middle. For cardiac muscle, it's different. The optimal length is the greatest distance, right? So it's going to start off very far from its optimal length, and the more it stretches, the closer it gets to its optimal length, the more force it's going to release. Think about it like a rubber band. So as you stretch that rubber band, the farther away you stretch it from its original shape, the more force it's going to generate to recoil if you let it go, right? And so the same thing happens with the left ventricle, or both ventricles rather. When you stretch them by filling them with blood, they generate more force, and then they're going to squeeze more blood out. So in this way, increased venous returns means increased stretching of that chamber, means increased stretch of or strength of contraction, which means increased stroke volume. If you fill that chamber with more blood, it's going to generate more force, it's going to squeeze more blood out. Okay, and that's what Starling's law is all about. All right, let's look at this graph here. And this pretty much highlights the same thing. So cardiac muscle, the more we stretch it, the closer it gets to its optimal length. And so the more we stretch this chamber, the bigger the end diastolic volume will get, and then the more stroke volume we will release because we're now generating more strength, more tension, more force as that muscle contracts. And so increased end diastolic volume means increased stroke volume. Right? Similarly, if we look at the influence of the sympathetic input on ventricular contractility, we would see that even if you kept the volume the same, even if you did not change the amount of volume that you're filling into the chamber, just by increasing the sympathetic input on this cardiac muscle, we will increase the stroke volume. So this graph tells us two things mainly. That sympathetic activity increases the stroke volume independently, and then end diastolic volume increases the stroke volume independently as well. Meaning that even if you kept the volume the same and you increase the sympathetic input, you would also increase the stroke volume. All right, factors that affect the stroke volume are going to be the filling time, which is influenced by preload. And filling time is a direct measure of what? Filling time is a direct measure of what in terms of the heart? Filling time is what time? What's the other measure of time in the heart? The heart rate, right? So filling time is a measure of the heart rate. How much time is the heart spending filling versus spending contracting? If we speed up the heart rate, the heart spends less time filling. If we slow down the heart rate, the heart spends more time filling. And so filling time is one factor that can affect the stroke volume. Atrial pressure, this is how much pressure the atria is squeezing blood into that ventricle with. If the atria is contracted more forcefully, it's going to squeeze more blood into the ventricle. We're going to eventually pump more blood out of the heart. So if you increase the filling time, you decrease the stroke volume. But if you increase the atrial pressure, you increase the stroke volume. And finally, central venous pressure. This is a little bit more complicated than we're going to go into it. Central venous pressure is the amount of pressure that's existing in your veins, the veins throughout your body. And this has to do with, again, your state, your body state, if you're obese, if you're not, if you're resting, if you're an athlete, that will determine how much pressure is on your veins to return that blood to the right atrium. If you're on bed rest or if you're not very physically active and your muscles are not contracting, you're not going to return as much blood into the right chamber. And if you're not returning much blood to the heart, eventually you're not going to pump as much out. Okay, so these are the factors that influence how much blood is pumped out of the ventricle. And lastly, afterload. Afterload is the amount of pressure that's in the aorta. So afterload is how much pressure exists outside of the heart, which is in that major vessel. And we talked about this as well on Friday. If there's increased afterload, this means there's increased resistance in those vessels, right? And if there's increased resistance in the vessels that are leaving the heart, are we going to pump more or less blood out? If there's increased resistance in the vessels that are outside the heart, are we going to pump out more blood or less blood? Less blood, right? We have a blockage, we have resistance. And so if you increase afterload, you decrease stroke volume. If you decrease afterload, you increase stroke volume. Okay, any questions on that? Any questions?
So you increase the heart rate or increase the filling time, you're decreasing.
All right, so if you increase filling time, sort of walk it through yourself in your head. If you increase filling time, the heart has a longer time to fill. More blood comes in, right? And so if more blood comes in, I'm going to pump out more blood or less blood. That's stroke volume. More, right? More is filled, more is pumped out. Same thing with atrial pressure. If you increase the atrial pressure, the heart, the atria specifically is squeezing harder. It's working harder. It's going to pump more blood down into that ventricle. And if you pump more blood into the ventricle, we're eventually going to pump more blood out. So increasing atrial pressure increases stroke volume. And the last point was the central venous pressure, CVP. If you increase the central venous pressure, more blood is going to rush back from all your veins into your right atrium. And that is going to affect stroke volume as well. Think about it this way. If the heart has more blood coming into it, it's only going to pump more blood out. If the heart has less blood coming into it, it's only going to pump less blood out. All right? Any other questions? These kind of take some getting used to. So practice going over the scenarios in the heart. They're all pretty much self-explanatory. So think about it. Think about the heart as a pump. Think about how hard that chamber would be working, whether less blood or more blood would be pumped out. All right? And so this last diagram kind of sums up all of that. So, cardiac output is a product of stroke volume times heart rate. And if you look at all the factors that affect stroke volume, there's end-diastolic volume, the amount that was filled into the ventricle at the end of diastole. There's contractility, right? How hard, how forceful the ventricle is working. And then there's afterload. So how much resistance exists in the aorta and the other systemic vessels. And then we know that contractility is influenced by the sympathetic nervous system. And we know that end diastolic volume is influenced by venous return. Okay, so venous return is the amount of blood that comes back, that venous deoxygenated blood that comes back into the right side of the heart. If we bring more blood into the right side of the heart, we're only going to pump more blood out.